So what I'm going to talk about today is trying to get computers to do things which humans are absolutely terrible at. And I think that's really important because a lot of the success of deep learning is about being able to reproduce kind of what the brain does. And that works really, really well for deterministic tasks. Like if I showed you all a picture with an orange in it and said, what's that? Every single one of you would know it was an orange. It's a deterministic task. Customer lifetime value prediction is absolutely not a deterministic task. It's an extremely stochastic, difficult problem. And to put that in perspective, I don't know what my own lifetime value to ASOS is. I haven't even got a clue. I couldn't probably be within a factor of 10. And I know more about me than anyone else in the world. So it's a very, very different kind of problem. And as I get into this talk, you'll see that the main solution to it isn't using deep learning. It's actually using random forests. But you can do better, a little bit better than a random forest by using some ideas from deep learning. How are we doing? Still another 3 minutes. I think I'll give it a little bit long before officially starting. But I suppose I could do a little introduction to ASOS if not everyone here has heard of ASOS. So ASOS is a fashion company which is primarily aimed at people in their 20s, although we sell a lot to people who aren't in their 20s as well. Our global headquarters is in Camden, where we have 3,000 staff, and we're 16 years old. And importantly, we're 100% an online business. So we have this massive 16-year-old data set of customer interactions, weblogs, return data, and such like. And we do some really cool stuff at ASOS. So last year, we fitted out the Paralympic GB team. Last year? Yeah. So they were coming in every day for about a month before the games to get their kit fitted. So it's a cool place to work. This talk has 3 main sections. So the first section, I'll outline what is basically the state of the art for customer lifetime value prediction. And then I'll move on to how you can take the state of the art and using techniques from deep learning, and we tried 2 different deep learning architectures, you can improve upon the state of the art. And then hopefully, I think it's quite likely that I'll get to the final part of the talk, which is the stuff that I'm really excited about, which is the extensions we're currently looking at to the state of the art to do some really cool things. Great. So as Susanna said, my name is Ben Chamberlain. I'm a senior data scientist at ASOS. But I'm also in the final year of a PhD with a machine learning group at Imperial College. The ASOS team are those 3 guys back there. So if you have any questions later on, I think they're here all day about any of this stuff, then please do go over and ask them. So this is joint work between Imperial College and ASOS. So the first thing to really clear up is what is customer lifetime value prediction. In an ideal world, what we'd do is we would know exactly every transaction a customer will make for the rest of time, and then we'll discount those cash flows so that cash flows today are worth more than cash flows in the future, and we'll just sum up the discounted cash flows, and that will be the customer lifetime value. And obviously we can't do that because we don't know how long a customer is going to last for. And so we find a proxy solution. I'll talk about that again in a bit. There are 3 big applications for us of customer lifetime value prediction. In fact, I would say of all of the customer profiling that we do at ASOS, lifetime value prediction is the key metric that we learn. And we use it to target 3 other metrics, which are kind of big business metrics at ASOS. Those are the churn rate, the customer frequency, and the average basket value. And the way we do that is by being able to predict how much customers are worth in the future, we're able to target them with increased levels of marketing resources to nurture really good customers, and at the same time, try not to nurture those customers that might not be so good. So we basically allocate our marketing spend, retargeting, or paid social advertising, or Google AdWords to the best kind of customers. The second reason why it's really important is that it allows us to value intangible things which are otherwise very difficult to understand how much money to spend on. And by that I mean, if you ever go on the ASOS site, you see we have things like fashion blogs on there. Also like what is it worth to open an email? How many emails should we be sending? So all of those things we can do by having some forward-looking prediction of customer lifetime value.
What's a bad customer?
What's a bad customer? It's being recorded, isn't it? So I'm very much under sort of ASOS PR rules here. So I would say a bad customer is someone that makes a large number. Well, there is no bad customer. But a less good customer is someone maybe who makes a large number of small orders that they ship separately. Good. Jump in with questions, feel free, anything that's really difficult like that. Customer lifetime value prediction has been studied now for at least 40 years. And the original models, they were very simple statistical models. They were called buy until you die. And in a buy until you die model, all you really try and do is you predict how long a customer is going to remain a customer for. And then you times that by the company's average basket value and by the average frequency of customers. So it's a super simple model. 10 years later, people were doing slightly more sophisticated models. There were these RFM models, which some people still use now. It stands for recency, frequency, monetary value. So now, instead of just trying to estimate how long a customer will last for, you have to estimate these 3 random variables, basically. So they're slightly more sophisticated models. They have 3 unknowns. However, fast forward to the age of the internet, and suddenly you have these enormous data sets, principally session logs, but also much more detailed transaction logs, returns logs. We have customer care logs as well. And these simple statistical models are no longer really fit for purpose. It's fairly obvious that by incorporating more data, you can produce better predictions of lifetime value. So you need models that can do this. And machine learning really is the answer to these sort of problems. You take something like a random forest. A random forest can easily work with 100,000 different features. So it's a very different game to these simple statistical models. So people have tried pretty much every big beast that's gone through the machine learning world. Machine learning roughly moves in decades. So in the decade of kernel machines, people tried kernel stuff. In the Bayesian decade, people tried Bayesian stuff. And now we're halfway through the decade of the neuron, and people like us are trying neural stuff. There have been a few papers which compare Bayesian, kernel, logistic regression, all of these methods, and overwhelmingly, the best approach to do customer lifetime value prediction and many other stochastic problems like this are random forests. There's a great paper by Groupon at last year's KDD where they sort of lay the ground for this, which I'd recommend you check out. There's a link for it, a reference for it there. So moving on to how we actually do a CLTV model. As I said earlier, you don't get to see your customers die, so you don't really know what they're going to spend. So you need a proxy for this. And our proxy is we say, okay, let's just use a year. So what we do is we take data from a year ago, we add up the net sales minus returns, and that's our label to train a supervised classifier on. Then we go back another year, we extract a whole load of features, we train a random forest so that it can predict those labels from the features. Then we keep all of the parameters, take last year's data as features, and then we predict what's going to happen over the next 12 months. There are 5 main classes of data that we use for these models and many other models like them at ASOS. Those are the receipts data, returns, the session logs, the customer care data, that's the guy with the headset there. So anytime you email, call, or tweet us, that gets logged. And then the final thing is we have some light demographic data. So we have age, gender, and location, but nothing else. I think currently we're using 135 handcrafted features. And the best of them are listed behind me there. So this is just done using random forest feature importance, which comes with most random forest packages. We do this in Python. And you'll see that there are features from all 5 of those categories. So there are some demographics in there. The number one, unsurprisingly, is number of orders over the last year. There's some session data in there. And there's a few fashion esoteric things. For instance, the number of orders you made from the new season is really important. It's worth saying at this point that this sort of stuff isn't the whole truth because it doesn't cover cross features and it also doesn't cover features that are really, really important, but only for a small number of people. So for instance, at ASOS, we have like the equivalent of Amazon Prime, we have a Premier service, which is free delivery. So people that have Premier, they spend 4 times as much as people that don't have Premier, but not many people have Premier, so you don't see it in this list. So you don't just throw away things that aren't in this list necessarily. One of the real challenges with customer lifetime value prediction is that the distribution of the spend of your customers is a really, really horrible one. So it's not like a Gaussian or anything. You'll find, and these are completely made up numbers, so these aren't ASOS data or anything, but a large proportion of your customers will churn, so they'll have 0 lifetime value. And then from there on, you'll have a power law distribution. So you'll have like a median at maybe 100, but then some people will be spending, and at ASOS this is true, some people spend millions of pounds a year at ASOS. And that is an extremely difficult distribution to fit with a machine learning model. So most machine learning models, you might use sort of like mean absolute error or squared error. And it'll tend to snap on right at the top there, which is the part that is the most stochastic, so the part that you actually care least about. And we found when we did this originally, we were just wrong for like almost all of the customers. So you kind of 30 quid over for the vast majority of your customers, which is no good really. And the solution to this problem, well, there are a few solutions. So what the Groupon guys did is they split their customers up into 5 different groups, and they trained completely independent models for each group. And the reason we didn't do that is because I think there's clearly a trend in machine learning now where better data beats more sophisticated models, and bigger data beats more sophisticated models. And so we didn't really want to throw away 80% of our data for each model. So what we do is we have a model which learns percentiles, and then we map from percentiles onto pound values. And there's a bit of subtlety in that. You need to calibrate this thing properly. And the details of calibration are in the paper, and there's a link for the paper at the end of this talk. Cool, so now moving on to the bit that I really probably should have been talking about from the start, which is how we apply deep learning to customer lifetime value prediction. Now, the beautiful thing about deep learning is that it automatically learns the features of the problem as long as you have a rich and complex data set, and ideally where the features are hierarchical. And we absolutely have that in these problems. We have this very, very complicated session data. So there are 2 classes of features. There are the handcrafted features that I talked about earlier. And for the handcrafted features, you have to have some domain knowledge to be able to craft them. I mean, not a lot. I guess you don't have to be a genius to know that the number of orders is important for how much someone's going to spend next year. But you have to have some level of domain knowledge. The diagram now on the right, that's a very simple, old-school convolutional neural network. And what that does is it learns increasingly more abstract features as you go down the layers. So the first layer there will just learn edges and simple shapes. The second layer, you might start to learn circles and squares. And then the third layer, you might have eyes. And right at the end, you have a representation of whole human faces. And that's kind of how these models work. They automatically learn features. And we experimented with 2 different architectures for automatic feature learning. The first one is a wide and deep model, which was popularized by Google a couple of years ago. So some guys from Google Play originally invented this. And the great thing about it is it's publicly available on TensorFlow, so anyone can just download it and use it relatively easily. And the second thing we tried was taking the random forest and using neural embeddings of customers, basically. So start with wide and deep. This is the wide and deep model. So the wide part refers to a really, really big logistic regression with lots of cross features. And the deep part is a deep neural network. And the idea here is that the wide network memorizes data, and the deep network is able to generalize. So by combining kind of memorization and generalization, you get something that's better than either of them. Or so they claim in that paper that's referenced there. And is that true? Well, yeah, actually it is. So we ran these experiments. We compared logistic regression, just the deep model, and then we added in the wide and deep model. So the AUSD stands for area under the curve here. And on the x-axis, those are the number of hidden neurons and the number of layers. So the first one is 2 hidden layers with 2 neurons in each. So yeah, we found that this wide and deep idea has some merit. you can do better by combining logistic regression with deep learning than you can with either in isolation. So that's great. So what next? How does it compare to using just a random forest? So here what we did is we tried different numbers of neurons. The red line at the top is the performance of the random forest, and the green line at the bottom is the performance just of logistic regression. The thing about deep learning is add more neurons, train for longer, you get better performance. That's pretty much a given. So you can train absolutely enormous networks with over huge periods of time and you will do pretty well. But should you do that is a completely different question in a commercial setting. So we calculated that we needed around 100,000 neurons to beat the performance of this random forest. So is that a reasonable thing to do? It really just depends on, can we run it fast enough? At ASOS, we're on Microsoft Azure Cloud, so we can basically spin up as many machines as we want. So really, time is out the window. You can convert everything to cost. Does it, I mean, how much does it cost? Is this a reasonable thing to do? So we ran some simulations. That red line there is the cost of the random forest, normalized, so at 1. And that dashed line you can see here is the performance of the random forest. So what we did is we estimated how many neurons we'd need in this wide and deep architecture to get the same performance as a random forest. And we realized it was going to cost us at least 100 times more than our random forest model to run. And we run this thing every day. And that's just not a viable solution for us. The benefit just doesn't outweigh the cost for the wide and deep model. So that killed that for now. And moving on to what I think is one of the most important applications of neural networks certainly in e-commerce. And that's these embedding models, which were originally popularized for.
Yeah, the previous one, I was just wondering why the random forest is just a single line. Have you tried to, increase the complexity of the random forest, add more trees, or I don't know, like?
Yeah, so what we did is we optimized the random forest for AUC. And then we used that random forest. So we had a baseline, basically, that we had in production, and then we were comparing this to the production baseline, as well as only a single line there.
And you just compared using, I guess, GPUs in Microsoft Azure?
Yeah, so GPUs in VMs, yeah.
Okay. So it takes about P100 or?
Yeah, M80, I think. But I could be wrong about that. Brian over there knows the details of this experiment.
We're a bit faster now.
Yeah, are you?
I am.
Yeah, okay, cool. Good, well, we can talk about that later. Okay, good. So this is the idea with neural embeddings, is that you learn the embeddings in an unsupervised way, so with no labels, and then you take them out, and you just stick them in as additional features to the random forest. So this is a very different architecture to the wide and deep model. Embeddings originated in natural language processing. There's this really super famous model called Word2Vec by Thomas Mikolov. When he was at Google, he's now at Facebook. It has to be one of the most successful deep learning models in the world. It's in Google's search engine. It's what your phone does when you talk to it. It really is everywhere. And people have done this stuff for nodes of networks, for items in recommender systems. We've done it for customers. There must be like 100 papers which are something 2Vec. It's really huge. It's so big that there's even a book on it, just on this one method in Japanese, but there's a book. The way it works is it takes categorical data like words, which used to be represented as one hot encoded, so there's a 1 and a load of zeros. And it represents them as vectors, maybe a 500-dimensional vector, which have the property that similar things are close to each other in the vector space. So this circle here is a 2-dimensional vector space. And these are the vector representations of these countries. And you see the countries are close to each other, but things that are unrelated, like kites and space, are far away from the countries. And that turns out to be extremely useful, both because it's much easier to compute in lower dimensions and because you encapsulate similarity, which turns out to be really, really important. This is the architecture of the Word2Vec model, or one version of it. It's super simple. So it only has one hidden layer and 2 massive matrices of weights. And they're massive in the sense that there are 100,000 words in English, roughly. So there are 100,000 rows, and you choose the number of columns, and it's normally about 1,000. So these are big objects. At the end, you use a softmax to get a probability of an output word given an input word. And then once you've trained this on maybe 1 billion words, you take out W in, and that becomes your embedding. And so each row of that is something you then just feed into your random forest. The inputs to Word2Vec are just a sequence of words. And you can use a sequence of anything to learn an embedding of anything. And so what we did is we took every product in the ASOS catalog and we looked at the sequence of customers that viewed that product. And that gave us a sequence. And then we just pull out our TensorFlow or our GenSim or whatever Word2Vec implementation you like, and you just stick that sequence in, and out comes an embedding of customers where similar customers, defined by customers that view the same sorts of products, are close to each other in an embedding space. And you get this AUC uplift, so it's a statistically significant uplift over just using the random forest. And because these things are offline, you can reuse them, so the training time is not as pernicious as using the wide and deep model. So it's a big win. And this is the architecture that we ended up having at ASOS. So we're on Microsoft Azure, we're using Apache Spark, our production code is in Scala, and then we have a TensorFlow embedding layer which feeds in to our pre-feature processing, and then out come a load of customer attributes. So that's our architecture. These slides are available, so you'll be able to have a closer look at that later if you want. And we've written a paper about it. This is appearing at KDD this year in Nova Scotia. So please, if you're interested in more details, there's a whole load of details in the paper. Great, so I've still got 5 minutes, which is wonderful, because now I can talk about some really, really cool extensions that we're looking at. Embedding models came from language, and in language, there's no concept of time. Words just follow one another. There's no idea that different words in a sentence should be spaced any differently. Now, that is clearly not true for a whole load of types of data that people have just basically used the embedding black box for. And that includes the data we're using, the customer interaction data. So we have a timestamp for every customer product view. And so at the moment, what we're doing is we're basically saying we're ignoring those timestamps and we're just pushing everyone to be the same distance apart. And that doesn't really make a lot of sense. Some of these interactions are a month apart, some of them are a second apart. And it makes sense that people who are interacting closer in time are more similar. Now, there's not really been any research done in this area yet. There's one paper by some guys at Yahoo, which is referenced there, where they mention in passing that they sample from 1 over the time. So Sophie, ASOS over there, is currently, she's also with Antwerp University, I think I got that right, yeah. So she's currently doing some research in this space to look at how we can incorporate time into these embeddings. And Duncan, who's also at ASOS over there, is looking at how we can use recurrent neural networks to incorporate this element of time. But I think that's a really big and interesting field which is going to produce much better embeddings for these kinds of data than we've seen so far. So I really like that. The second big extension for me is quite complicated to explain, but I'm going to try anyway. So going back to these models here, these two matrices, they learn vector representations of words or customers or products or nodes. But those vectors are implicitly Euclidean vectors. So Euclidean meaning a flat space where all the things you know about geometry are true, like Pythagoras' law. A Euclidean space isn't the only space. So there are two other relatively simple spaces that you can learn vectors in. One is spherical space. So if you imagine the surface of the Earth is a 2D spherical space, that's positively curved. And the other kind is hyperbolic space, which is negatively curved. If you imagine the saddle on a horse. And recently, people have shown that hyperbolic space has some really amazing properties that apply to complex networks. So a complex network is one that has, like Facebook, so it has power law degree distribution. Some people have 100 million connections, but most people have 10. And it also has clustering, so you get groups of people that are very tightly interconnected. Now, this is exactly what we find when we look at the network of products and customers at ASOS. It's a complex network. It has very high degree people, very high degree products, and also clustering. And so what we found is that actually the appropriate embedding space for our customers is not this Euclidean space that everyone has used in the past, but it's actually it's a hyperbolic space. A hyperbolic space it's much bigger than a Euclidean space. And so what you find is that the really high degree vertices sit in the middle, and it has enough space around the outsides for all of the lower degree vertices. So these pictures here, they're MC Escher, that's called Circle Limit 3. He's an artist from about 200 years ago, around the same time Poincaré was doing this work. And all of these tiles are the same size in hyperbolic space. So they shrink to 0 as you get to the edge in Euclidean space, which is the one we're looking in. But that's because hyperbolic space gets larger and larger and larger as you get to the edge, and the edge is at infinity. So certain things just fit better in hyperbolic space. Good. Well, that's something I'm very passionate about. I can see that no one else really is, but maybe you can ask me questions about it later. And maybe I've gone too far with that. Anyway. Good, well, that's my last slide. So if you have any questions, please do fire away now. Thanks very much.